functions with successive differences. So we've been looking at a variety of different types of functions. We've looked at linear functions, quadratic functions, and exponential functions. And each function has its own pattern to it. Each function has a pattern to its data, it has a pattern to its equation, it has a pattern to its graph. So let's take a look at those and see if we can identify what type of function it is from the patterns that we recognize. So a linear function has an equation that's y equals mx plus b. On a coordinate plane, we would see a line, a straight line. A quadratic function has this pattern in its equation, y equals ax squared plus bx plus c. And when we graph it, we'll see that parabola shape. And an exponential function has an equation that looks like y equals a times b to the x power. So that domain, that input value of x, is our exponent. B has to be greater than 0 for this to be an exponential function. And we see this, roller coaster shaped to it here. All right, what we're going to do, we're going to graph each set of ordered pairs. We're going to determine whether the ordered pairs represent a linear function, a quadratic function, or an exponential function. So pretty straightforward. We're not doing anything fancy here. Take your ordered pairs, plot them on a coordinate plane, see what pattern you find. So when I plot these ordered pairs, I end up with a very straight line there. So this is a linear function. My second set of ordered pairs, when I graph those, I see that parabola shape showing up. So that's a parabola, which makes a quadratic function. Graphing, pretty straightforward. How can we tell from just a table, however, if I don't graph? So look for a pattern in each table to determine which model best describes the data. So the first thing I want to look for is that my x values have a consistent pattern to them. I'm going to see what the pattern is in the y values to determine what kind of function it is. My x values, I would really ideally like them to have a pattern of increasing by 1. That's ideal. But if that's not the pattern, we definitely want to make sure there is a consistent pattern to them. At that point, I'm going to see what's going on with my y's. And these outputs are pretty straightforward. I'm going to be subtracting 1 every time, which means there's a common difference. I'm basically adding a -1 every time. And since I am basically repeatedly adding, that's the same as multiplying. I've basically got a slope here. This is a linear function. So there's my common difference, linear function. And my last one here, again, I want to check to make sure that my domain has a consistent pattern there, and I'm adding 1 every time, so we can look at my output values, my y values. And here I see I'm not adding the same thing every time, but I am multiplying the same time. So if I do my 2.5 divided by 6.4, I get that I am multiplying by 0.4 or 2/5 every time. So I do have a common difference here, a common ratio. We're multiplying repeatedly, and we know that repeated multiplication is exponents. So this is an exponential function. So we should be able to identify a linear function, a quadratic function, or an exponential function based on either a graph or the patterns that we're seeing in a table.